Everybody's Achilles heel, or the majority on AGK. Most people can muddle their way through engines and propellers and air conditioning, but electric seems to be, you know, magic. There's nothing magic about it. It's pretty straightforward, and I hope I'll keep it simple for you. I have to keep it simple for me, you see. All right, electrics then. Some basic theory applicable to AC and DC electrics, and a few ground rules and terminology to look at. When we talk about the flow of electrons, we've got ourselves an atom here, and the atom consists of a nucleus of protons, which are positively charged, and neutrons, which are neutral or uncharged. And then whizzing around the outside of those, we've got these electrons. Electrons are negatively charged. Now, if we have an electron crashing into this one from the neighbouring atom, it forces one of these out into that one. And that forces one out into that one. Because they can't hold any more than that. That's how many we're supposed to have, therefore they must stay like that. So we set up a flow of electrons. Now you'll note that those are negatively charged. So in reality, electron flow is actually from negative to positive. But every time we look at a basic electrical circuit, we presume, don't we, that it flows positive to negative. And the reason for that is that that convention was already established before they discovered what was really going on with electrons and worked out that we've been doing it the wrong way round for 150 years. Okay, so there is a question that comes up on that, which we'll look at shortly. Now, when we push these in from one to another, the analogy we can use is perhaps this one, of ball bearings in a pipe. If we push a ball bearing in this end of the pipe, another one has to come out that end straight away. There's no alternative, is there? It has to happen. Or water in a hose. If you turn the tap on, the water coming in this end forces the water already in the tube out. It has to flow. The movement is quite small, but the result is instantaneous. You know, the electrons themselves don't move very far, but the effect is of a very rapid reaction at the other end. The current, when you make a circuit, current's travelling at 3,500 miles per second. So around the world in 7 seconds, i.e. quite quick. Right? That's all we need to think about really, it's quite quick.
It's not the speed of the light. It's the speed of the light.
I don't know. Is that the same as 3,500 miles a second? No. The speed of light's faster than that, isn't it? 300 million metres per second, isn't it? Yeah, so no. The electricity, electron flow, 3,500 miles a second. So watch out for that key word there. Electrons in the circuit actually flow. Where do they actually flow then? Negative pos, and we call it? Okay, so answer 2, yeah? Now let's get back to reality, the one we've been using for the last couple 100 years. Seems to work perfectly well, and that is that it flows pos to neg. Okay, when we've got ourselves a basic circuit, we require a force to move that current around the circuit, and that force is electromotive force, or volts, or potential difference. That is our force. Electromotive force, potential difference. Let me try and explain it this way. If I've got those ball bearings in the tube and shove another one in here, another one's going to come out the end. Yeah, that's fine. But if we make the potential difference bigger, keep them like that, they're not going to want to flow very fast. Put it like that, and the water wants to flow very fast out the tube. The bigger the potential difference, the greater the current once you establish the circuit. Okay, that's just a way of thinking about it in an analogy. Also, we talk about the load. In this case, in our very simple circuit, we've got a battery, the symbol for which is a long and a short, positive terminal and a negative terminal. We've got a switch to complete the circuit, and we've got a resistance load. In this case, our resistance load is just the light bulb. Okay, so what we then do, we maintain continuity by completing the circuit, and that makes the light bulb come on. Remember, current, if you see that in a question, current can only flow where there's a circuit. There's no current flowing there. There's voltage in our battery. There is a potential difference. It's a potential so that when we establish the continuity, now current can flow, and now we can use some of that power, some of that current to work our resistance loads, to power the devices that we want to power. Simple. When we have a circuit flowing like that, in a direct current circuit, the current would flow in one direction only. Okay. If it's an AC current, once the circuit is complete, the current flows both ways all the time that circuit is made. So DC, one direction flow, AC, alternating current flows both ways. We'll look at that in a bit more detail. A few basic definitions then. Volts is the potential difference or the electromotive force. Now the symbol for volts that we use is V. You will also see U. Actually, U is the potential difference, so we could say that U is equal to 24 volts. We would never say V is equal to 24U. Likewise, when we come to amps, the symbol is I, or A, so we would say I is 6 amps, but we wouldn't say A is 6 I's. Right? So if you like, I is the concept, and A is the value. Ohms is the resistance to flow, and for the symbol is omega or R. So again, we could say R equals 8 ohms. We wouldn't say ohms equaled 8 R's. Which leads us neatly to Ohm's law. Ohm's law is one of those magic triangles that we love to hang on to because it makes life simple. If we want to know the value of any one of them, we cover that one up and the answer is V over I. If we want to know the value of I, we cover it up and V over R equals I. So volts is amps times resistance. Amps is volts over resistance, and resistance is volts over amps. Simple, isn't it? Let's have a look. I'll stick our triangle up on the board just as a reminder for this next little bit, VIR. Okay. Current is 6 amps, resistance is 3 ohms. Funny, I thought resistance was futile. Okay. What's the voltage then? These are all fairly simple mental arithmetic problems. What do you make it, Jason?
18.
How much?
18.
18, yeah. Make yourself say the label as well. Make yourself say 18 volts, because you can be sure that 18 amps will be there as an answer, or 18 ohms will be there as an answer. Make yourself say it, even if it's carats per cubic fortnight, 18 carats per cubic fortnight. Make yourself say the label and you'll get the answer right. Okay, 18 volts, correct. Current is 4 amps, voltage is 12 volts. Resistance is what? Martin?
3 ohms.
3 ohms, excellent, yep. Resistance is 12 ohms, voltage is 36 volts. The current, therefore, Matt?
Yeah. Sorry. I don't know without a calculator.
Just put the numbers in the triangle, that's why I've left it up here.
Yeah.
Yeah? So, 36 over 12 is?
3
Amps.
Yeah.
Amps, yes?
3 amps.
3 amps. Okay. Got the concepts? When you see if you draw that on your bit of scrap paper, and then just replace the letters with the numbers in the equation, and you've got the answer there for you. That's simple. Electromotive force is measured in one of those units, and current is measured in another one. Which are they? Jim?
3
Volts and amps, thank you, sir. Okay, when we make current flow through a conductor, we have some current flow effects to think about. The 3 effects of current flow are heat, and if you don't believe putting current down a cable makes it hot, try giving your mate's car a jump start when it's a cold morning and then pick the leads up afterwards. They're hot. light, normally in the infrared band, so you won't see it, but light will be around that when you're making a current flow, and magnetism. Now, the resistance of a conductor or a cable, the resistance is directly proportional to the diameter. If we think about it, a fat cable that has low resistance. Use the analogy of water again, and replace the volts with our water. If we're going to put that 1,000 litres of water down a 1 metre pipe, there'll be very little resistance. Try putting 1,000 litres down a drinking straw and see how much resistance you get. It'll take forever to do the job. So thin cable, higher resistance. The length of the cable is also directly proportional to the resistance. A short cable has low resistance. Logically, then a long cable, a high resistance. You can have considerable loads or voltage lost just from one end of a cable to the other. And the material is important. If you've got materials with a positive temperature coefficient, where resistance is directly proportional to temperature, things like copper or your metals we use as conductors, if we make current flow through them, bless you, the temperature will increase, which makes the resistance increase. And as the resistance increases, remembering Ohm's law, if the resistance increases, the amps has got to decrease, hasn't it? Yeah. So why does that happen? Let's have a look at it. When we look at our piece of shiny metal, you know, that appears to be nice and shiny, yeah? So that would be nice, clean bit of metal. However, it's not that straightforward. What looks like a shiny piece of metal, if we examined it microscopically, would be more like that. And when we make a current flow through it, heat is one of those secondary effects. What that does is it makes the peaks harden or heighten and the dips deepen. So actually we're expanding the surface of the conductor and making it have to travel further. We're increasing the resistance. So temperature increases, resistance increases, current flow decreases. That's a positive temperature coefficient. Materials with a negative temperature coefficient behave very differently indeed. These are your semiconductors, graphite, ceramics, carbons. They have a different story altogether. They don't do that, okay? Or they don't do that, I should say. So we put current down one of those, the temperature increases, but the resistance decreases. And if the resistance decreases, what happens to the amps, the current flow? It has to increase, doesn't it? Hang on, if the current flow increases, what happens to the temperature? So we've now got a cyclic event. The more we're putting down here, the hotter it's getting. But the designers can use that characteristic to their advantage. Just be aware that the two are very, very different. What do you say, Charlotte? Yep. Okay, we talk about resistance loads. We use the light bulb as an example. It could be 3 light bulbs. It could be, 3 light bulbs, a motor and a heater. We've got resistance loads in a circuit. If we put our resistors together in series, connecting them positive and negative all the way through, the maths is very simple. We simply add them all up. And even I can work out that 1 plus 2 plus 3 is in fact 6 ohms. What, Charles? Now there's a flaw with having resistance loads in series. We touched on it yesterday with our thermocouple, didn't we? We said that if we have them in series and one fails, we break the circuit. So you'll have nothing at all from that whole circuit. So your loads in an aircraft tend not to be wired in series, they tend to be wired in parallel. And when we wire them in parallel, some magic takes place. Those 3 resistors, a 1, a 2 and a 3, make 6 ohms. If we wire them in parallel, here's where the magic takes place. Okay? Firstly, if that should fail, these 2 are still going to work, aren't they? So that's a good thing. We'd rather all the systems keep working in the aircraft. But here's the magic. Now the reverse is true, it's an inverse relationship. So 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, I can get my head around that as a basic concept. I'll take that as read. Let's put some numbers on it then. So that means that 1 over R total is equal to 1 over 1, 1 over 2 plus 1 over 3. Right, so 1, a half and a third, yeah? So what's that going to be? 1.83, if we're doing it in decimals. So 1 over R total is equal to 1.83, which means R total is equal to 1 over 1.83, because we've just transposed that formula to find out the value of the total resistance. And look what's happened. The answer we get is less than any one single resistance load. Magic. So the more resistors we put in a circuit, the less the resistance is going to be. Magic. There is a simple solution to the question of two resistors in parallel, especially if you're British, because you're familiar with the flags of the home nations. You could say R total is equal to R1 over R1, sorry, R1 times R2 over R1 plus R2. And in that case, it's the flag of Scotland being north of the flag of England. If you like it, fine. If not, you can still use the original formula for it. So using that, what would be our total resistance in that then? Anybody? 2/3, yeah. 0.66 if you like, decimal wise, exactly. Stunned silence. Are we all happy with that? Excellent. The examiner doesn't use the shortcut here, he wants you to identify the correct formula. He calls it REQ, resistance or equivalent resistance. So the rec is equal to, which of those looks familiar? Number 4. Yeah, 1 over R1 plus 1 over R2. Happy? Power. Remember from our definitions on engines, power was the rate of doing work. And it was measured in watts. For the symbol for watt is W. Power is amps times volts. But hang on a sec, we know another answer for volts, don't we? What's V equal to? Sorry? IR. So, V is equal to I times R. So we can simplify that to say that power is simply I squared R. It's another useful expression. For example, current is 2 amps, resistance is 6 ohms. What is the power? Well, I squared times R. So 2 2s are 4 times 6 is 24 watts. Happy? Dead easy. Now if we want to know the voltage or the amperage going for a circuit, we measure it. And we can measure it with a device called the ammeter. In this case, an ammeter in series will be set up to read amps that are flowing through the circuit. A voltmeter is actually an ammeter but wired in parallel and then calibrated in volts, that's all. An ammeter on an aircraft can be a 0 centre or a 0 left, so we're showing a rate of charge or discharge there on this one, or we're just showing from 0 to the number of amps flowing through a circuit. Now, here's a question to test the old noggin. You're fitted with a 0 centre ammeter indicating 10 amps. If the loads are wired in parallel, switching on more loads, the ammeter would do what? What do we know the effect of putting more resistance load on?
Decrease
It'll decrease what?
resistance.
It'll decrease resistance, which will do what to the current flow? There we go. Magic, isn't it? This is a static charge. Static charge with an accumulation of electrons. You get a negative charge attracted to a positive charge and vice versa. When we talk about charge, we use the unit of coulomb. A coulomb is one coulomb in 1 second is equal to 1 amp. And we'll meet coulombs later on. Okay, basics. Happy with the ground rules? DC then. I think most of us, if we start thinking about DC electrics, our minds first turn to batteries, because that's a basic source of DC power, isn't it? Okay. What is a battery then? A battery is a store of energy. It stores chemical reactions that gives us electricity. It consists of cells. Each division here, that is a cell. There's another cell. Various types. We're going to look at primary cells. We're going to look at 2 types of secondary cells. Your aircraft battery is just used for starting and for emergencies if you lose all other power. Your basic primary cell, your torch battery, that consists of a positive and negative terminal, the positive terminal a bit in the middle, and the outer casing is itself the negative terminal. And inside we've got a carbon rod, and in this case an ammonium chloride electrolyte, which is just a way of storing the electricity chemically. Of limited application to us, but that's just the concept of a primary cell. Not rechargeable. You can get other types, of course, NiCads, lithium ion, lithium hydroxide, loads of different types of battery, but your basic primary cell is not considered rechargeable. Definition of an aircrew torch? Anybody? Cylindrical receptacle for the carriage of dead batteries? It's always dead when you really need it, isn't it? Okay. Secondary cell, in this case a lead acid battery, consists of a positive plate of lead oxide and a negative plate of pure lead. And in between we have an electrolyte of sulfuric acid, dilute sulfuric acid, in a casing. And you can see that each cell is connected to its neighbour and then connected to its neighbour again, in series in this case, to give us the sum total through the battery. Rechargeable. If you want to recharge it, you've got to put in more than the value of the volts. So to charge a 12 volt battery, you need more than 12 volts, and we'll look at how much more. The 2 main types of secondary cell we use in aircraft are lead acid or NiCad. This one here is a basic lead acid battery. I'll pass it around. Warning, it is heavy. No shit, it's full of lead. Okay, how much energy we can store in a battery is a measure of the amp hour capacity, ampere hours. If a battery has a theoretical 100 amp hour capacity, it means it can deliver 1 amp for 100 hours, or 10 amps for 10 hours, or theoretically 100 amps for 1 hour. If you ever discharge the battery at that rate, you burn it out, you completely destroy it, because there's a thing called a safe rate of charge and safe rate of discharge. You won't be asked about those. But that's the amp hour capacity. So the voltage is the potential difference in it, and the amp hour capacity is how much energy it's storing. Yeah? Ampere hours, number 4, yes? So the lead acid, lead peroxide positive plate, a lead negative plate, sulfuric acid electrolyte. Offload, before you connect them up, they've got 2.2 volts offload per cell. As soon as you connect it all up together, on load it becomes 2 volts per cell. So nominally it's 2 volts for each cell of a lead acid battery. So the one that's doing the rounds at the moment has 6 cells, so it's a 12 volt battery. They've got a steady rate of discharge, which is to say that if you take the amount of charge in the battery over time, it will decline fairly constantly. which means that it's got less usable power halfway along. But that discharge is measurable. You can measure it chemically. You can measure it with one of these things, a hydrometer, and literally squeeze that into the cell, pick up some of the electrolyte and measure the specific gravity. We'll have a look at the numbers for that because a question comes up on it. Okay, there's our engineer doing his specific gravity check. If it's charged fully, the specific gravity will be between 1.25 and 1.3. If it's low, it'll be between 1.2 and 1.24, and fully discharged, it will be 1.17. Bear in mind, water is of specific gravity of 1. You know, we're talking about a very weak solution by the time we get to a fully discharged battery. That's not a pilot task, that's an engineering task, so you wouldn't ever be expected to do that. But just so you're aware of it, and the fully discharged number does come up as an exam question. What have you got in the aircraft to give you some idea of the health of the battery? Voltmeter. And how would you actually deduce the health of the battery from that? Just from the voltmeter? Yeah, absolutely. Put a known load on it, i.e. stick a light on or stick a pitot on. If the voltage immediately drops to 0, then you've got a dud battery. If it falls slightly but then stabilises, the battery's healthy. Disadvantages of a lead acid battery. Well, a bit of a clue, lead, it's heavy, certainly heavier than NiCad batteries. Another clue, acid. Acid is corrosive. If the casing should split, and they do if they cook off, then you're going to have acid all over your aircraft, which is probably not a great idea. The voltage that the battery is capable of storing reduces over time. And in fact, it reduces over time and seems to be seasonal, doesn't it? Our batteries only ever fail when it's midwinter. They've got a slow charge rate. Safe rate of charge is something like 8 to 10 hours to charge a battery from fully discharged to fully charged. Here's an exam question. SG of a fully discharged battery is what?
1.
Yeah, 1.17. So, the other major battery, and the one that most aircraft use, a nickel-cadmium battery. It's got a cadmium positive plate and a nickel oxide hydroxide negative plate. Not, as your books say, a nickel-cadmium plate and an iron plate. All right? Those are the two correct metals for a nickel-cadmium battery. I'm rewriting AGK at the moment and finding all these little errors. The electrolyte is a potassium hydroxide gel. Now these cells aren't as powerful as your lead acid cells. They only produce 1.3 volts offload, and when you connect them up as a battery, they produce 1.2 volts on load. But here's the good news with the nickel cadmium battery. It's got a positive or a constant voltage on discharge. So on this one, what you get with a NiCad is you've got constant voltage, and then it falls off a cliff. It doesn't hold the power for any longer than a lead acid, but you've got usable power through much longer life of it. And that discharge is measurable chemically. So let's have a look at the advantages of it. Where does it win over lead acid? It's got a wider temperature operating range. Lead acid batteries don't like the cold. Constant voltage until almost discharged, as we've just seen. There's no acid to spill and damage your aeroplane. They can be charged much, much faster. And unlike a lead acid battery, which must be charged while it's in storage, a NiCad can be stored discharged, so it's much safer to handle. And they're normally in a sturdy metal casing. Disadvantage is NiCads can suffer from something called thermal runaway. Okay, the metal casing of a NiCad battery looks a bit like an ammo box. You've got these over-centre latches here, you've got vents which are normally connected to pipes to vent any harmful gases overboard. Standard aircraft type connector for it in there, and if you were to take the lid off of that, what you'd see inside is a whole bunch of individual nickel cadmium cells connected up by these bridging bars, one to the other, in series to give us the required output voltage on the battery. Now, they have to be taken out, cleaned and checked periodically because that can happen to them. That's a result of thermal runaway. Not good. But much safer than lead acid batteries in the long run.
What does it mean to run away? What happened?
It's when there's an internal fault in the cell and it just takes more and more charge until it overheats. Lead acid can do the same. I've had lead acid batteries boil on my boat a couple of times. And trust me, you don't want that either. You don't want boiling sulfuric acid fumes. But certainly thermal runaway on that will ruin the battery.
Would they be lighter than the lead batteries?
Yeah, they're not as heavy. They're not as heavy. You know, the materials in them are lighter than lead. I mean, big heavy sheets of lead there. But then you need more cells, so it's a bit of a balancing act. But they're just overall safer. To protect against aircraft catching fire because of that, you need a battery control circuit with NiCads. That will protect against overheating and overcharging and any internal short circuit. So that's just happening in background and you've got no control over that. Now with any type of secondary cell, if you want to charge a battery, you've got to put more in than it's worth. If I had a 12 volt battery and connected it to a 12 volt output, nothing would flow. They would just stay, you know, it's like if I've got 2 glasses of water and I fill them both up, they're just going to stay there. What I want is the water to flow from that one to that one. So I need more in this than I have in here. Average is 112% of the on-load voltage. So for a 12 volt battery, we need to put 14 volts in to charge it. And most aircraft are 28 volts nominal and the battery is 24 volts. If you didn't have that extra 4 volts, it wouldn't charge. Good rule of thumb is 2 volts for every 12 to charge. Okay. What do we reckon?
Hey.
Hey, yeah. They charge much easier and they've got a constant output voltage. We know they've actually got a higher risk of thermal runaway than a lead acid battery. So anything with a 1 in it can't be the right answer. Remember the voltmeter's there to monitor the battery and system voltage. We've talked about the on-load check already. If you're discharged, the voltage will drop straight away. If you've got a dead cell, it will go to 0. Just like inside a battery where the cells are connected to give us the required output voltage, we can connect batteries together to give a required power. If we connect in parallel, the volts remain constant, but the ampere capacity is summed. So these 3 batteries connected in parallel, positive to positive to positive, give us an output of 24 volts and 150 amp hour. If we connect exactly the same batteries in series, pos to neg, what we end up with is in 72 volts, but only 50 amp hour capacity. And in fact, for some applications, you can have a series parallel connection. You know, military Land Rovers that run radios in them have 4 batteries connected in series parallel to give, you know, the sum, double the voltage and double the amp hour capacity of any one battery. Okay. Now, when we take power from a battery into a circuit, we've got to complete the circuit. We've actually got to make it flow. And in the early days, when aircraft were made of, you know, wood and canvas and stuff like that, you needed a cable to return the earth to complete the circuit all the way around. So you had to have a dipole system. There's your battery, multi-cell battery. There's your generator, there's aircraft loads, and you'd have to have another cable to make the return. A dipole system, 2 poles. Once the aircraft start being made of metal, it's very much easier. Just like in your cars, you can connect the loads through the positive circuit, and the negative circuit is just a single pole earth return. So the one side is connected to the feed, the other side is just connected to the chassis, and that completes the circuit. Clever. The advantage of the single pole system, of course, is it's lighter and cheaper. There is a flaw with it, and that is that if any of these, if the cable to this, for example, were to chafe through, we're then going to have a short circuit, and if that contacts the aircraft's chassis, we've now got a short circuit, which is a fire risk. Which is why they're so careful with where they route cables and how they're secured. Generally, we distribute power around an aircraft by using buzz bars. So in this case, we've got a generator here, which is powering to a buzz bar, and we've got a battery here, which can power the buzz bar. When this generator is running at 112% of the battery voltage, it's charging the battery through the buzz bar. And our loads that we want to take off, we just take off the other side of the bus bar. Okay, it's from the Latin omnibus, omnibus meaning everything together. Buzz bar, that's it. Okay, electricity and magnetism. We remember this from our instruments, of course, the magnetic flux around the magnet. And we've also said, haven't we, that if we put current through a conductor, we're going to have magnetism involved. Basically, if you've got an electromagnet and can control the current, you control the magnet. The more current you put through it, the more power there is in the magnet, the magnetic flux increases. Now, the current flows through a conductor in direction of travel following the corkscrew rule. So basically, if I've got current flowing through this conductor, it's flowing, the magnetic field is coming around it in a corkscrew fashion in the direction of travel. Okay, so if I make a coil of wire, I can make myself an electromagnet. Bloody marvellous. If I then put a soft iron bar inside that coil of wire, every time I put current to it, that becomes a powerful, controllable electromagnet, and every time I turn the current off, it stops being a magnet. Because soft iron loses its magnetism readily. Hard iron keeps it. Okay, whoopee-doo, I hear you say. What am I going to do with that information? What I'm going to do with that information is use it for solenoids and relays. Excuse me, double click. Thomas, go slow. Come back. Thank you. Okay, there's a coil. There's a piece of soft iron. We energise the coil and we make that a magnet. We de-energise it and it stops being a magnet. We've now got ourselves an electrical method of turning something on and off. So we can control valves with it, we can control switches with it. A solenoid, just an electromagnet, simple as that. We can also use it in dole's eye magnetic indicators. We looked at those on the fuel panel the other day, and as you can see here, yeah, we complete the circuit, energise that, this becomes a magnet, break the circuit, it's no longer a magnet, the spring wins. Simple. More reliable than a bulb, less likely to fail, and as you've seen, can be used in a schematic to show the flow of something. Fuel flow, electrical flow, anything like that. A relay can be used to remotely switch circuits with much higher current in. Again, we complete the circuit of the coil, that becomes a magnet, attracts the contact, stop it being a magnet, and the spring wins again. And the designer can decide whether that's going to fail open or fail closed, whatever it needs to do really. John? Yeah. Magnetically operated switch. Okay. Let's have a look at one of the most common applications for electrics in any aircraft, and that's motors. Motors were discovered virtually by accident, as we'll see in this short video clip. And just pay attention to the second half of it, where he links motors to generators.
Across Europe, scientists were experimenting with Volta's battery, and in 1821, Hans Christian Ørsted uncovered some very unusual behaviour. While preparing for a lecture, Ørsted noticed that when he connected a copper wire to a battery and held it near a compass, the needle moves. That may not seem much now, but that's the beginning of electromagnetism, the first demonstration that electricity and magnetism can create motion. Faraday used these two critical discoveries to tap into the universe's very own power system. Here in his workshop at the Royal Institution, Faraday showed that electricity, magnetism and motion are all firmly linked. Just a year after Ørsted's discovery, Faraday designed this. There's a wire that goes into a pool of mercury to which a magnet is attached, and when you pass a current through that wire, watch what happens. Believe it or not, this is the world's first electric motor. 10 years passed, and with proof that magnetism and electricity could drive motion, Faraday made an incredible intellectual leap. If electricity and magnetism can create motion, Faraday thought, could the reverse be true? Could motion and magnetism create electricity? Well, he answered that emphatically with this rudimentary device. This pole in the middle is a magnet, and there's a tube here in which he's wrapped around copper wire and covered it with cloth and attached two small lights. Now, watch what happens when I move the coil through the magnetic field. I know it looks ridiculous, but what's happening is quite amazing. The light is lighting up, and that means electricity is being generated in the coil by just moving through the magnetic field. What Faraday had created here is the world's first electricity generator.
Hell of an intellectual leap, wasn't it? Okay. So we're looking at motors here. I neither know nor care much for Fleming and his right and left hand rules. Okay. If you want to use them, please do so. But I can give you a nice, simple way of getting it for the exam. Fleming's left hand rule is used for motors, and Fleming's right hand rule is used for generators. And the way to remember it, call them generators. Okay? Left hand rule for motors, right hand rule for generators. Effectively what he's saying there is the middle finger points in the direction of the current flow around the conductor. The first finger points in the direction of the magnetic field, and the thumb points in the direction of the resulting motion. So, if we make current flow through this coil here, through a magnet, the result will be rotary motion in this direction. That's the sort of question you're going to get on Fleming. Three. Yeah, Fleming's left-hand rule. Okay, so how we then control that is we attach a carbon brush through which we allow the current to flow into this commutator here, and then around there to the circuit on the other side, and the flow then comes out. And the resultant motion, as we've seen, is like that. And we break that commutator so that we're not making a complete circuit there. So really we're making one circuit in that whole setup there. Actually that's not enough. That would produce some fairly feeble movement, a bit like Faraday's first motor, you know, a bit of wire whizzing around in a pool of mercury. What we do is we put lots of coils, each one of those is a complete circuit from there right around to the other side, and we put it inside a very powerful electromagnet, so we control that by a winding on the magnet. That means we've got control of that, other than just leaving it to a permanent magnet to do the job. And even that would be fairly feeble, but if we repeat the process many, many times, what we end up with is a proper typical DC motor. If you've ever taken a DC motor apart, that's pretty much what you're looking at. You're looking at the commutator, the split ring commutator here. You're looking at many, many, many hundreds of windings, around these around each of these poles. You're looking at a very powerful electromagnet either side of it. So when you put your current through there, you're going to make quite a lot of turning force, quite a lot of motion through that. Now the windings are really quite critical, how they are wound in the circuit. If we wind it in series, okay, so the current flows first from through the series field coil to energise the magnet and then to the armature. Okay, you can see there all of the input flows through the field windings. It's just a few turns of thick wire, which gives you a high starting current and a high starting torque, but the speed of the motor would reduce as the mechanical load increases. So it makes it suitable for things like starter motors where you need a high initial torque requirement. Ideal for that, but not much use for a motor that's going to keep running for a long time, because as the loads increases, speed would reduce. So that is a series wound motor. Now if we take the field coil and now put it in parallel, where we call it a shunt coil, only part of the input's going to flow through the field windings. You can use many turns of thin wire for a shunt coil, and then it can only be started on low load. You haven't got that grunt high torque of a series wound motor, but it gives you a constant speed with an increasing mechanical load. So it's useful for things like fans, rotary inverters, anywhere where there's a pretty constant load.
So Chris, sorry, I missed that. So the shunt field coil, the difference is what, that it's in parallel?
Yeah, series coil is in series,
Right.
a shunt coil is in parallel. So you can call it a parallel wound motor or a shunt wound motor, it's the same thing.
We relate that to the original picture, the motor, previous.
That one there?
Yeah.
Well, you can't, because you can't see where that's connected to.
No.
It depends. If the current comes in through here, then goes through the armature and to the other side, it would be series wounding. If that comes in parallel with that current there, then it's a shunt wound motor. A compromise between the two would be to have a compound wound motor. Your books probably still say compund, but it's compound. It's being rewritten. A compound wound motor has characteristics of both. 60 to 70% of the magnetic flux is from the shunt field, because that's many turns of thin wire, and it gives you a constant speed under load and a good starting torque. So this is a good general purpose motor, sometimes called a split field motor. Okay, the sort of question the examiner is going to test you on with these is stuff like this. Remember, shunt wound and series wound. What do you say, Faisal? Absolutely, sir. Many turns of thin wire. Yep. If it was the series wound generator, then it would be relatively few turns of thick wire.
What about primary windings and secondary windings? That comes up, I think, this question.
That's on a transformer. We're coming to that. Okay, so we've got a motor. One of the most common uses, apart from starter motors, one of the most common uses for motors in aircraft is actuators. Electrical motors that move control surfaces, for example, will be actuators. They can be rotary actuators, where you have a motor inside turning a rotor to actuate something, typically around about 340 degrees of turn, and a limit switch which stops its movement, and actually when it gets to the end of that limit switch, it changes the polarity over, ready to return back the other way, and it can do that very quickly indeed. A linear actuator, also known as inching control, basically the motor's inside the screw jack and turns the thread on the screws themselves to move in a linear motion. Oh no, you didn't want to see that. I've just seen Microsoft PowerPoint has stopped working. Oh good. just see what happens. That's what happens. It's restarting. Apologies for the pause. I tell you what, let's take a break now while this is rebooting.